read questions from the Q&A box in chronological order. Thank you very much, and let's get started.
Great. Thank you, Shreya, for the introduction, and thank you to the Energy Hack group for setting up this event. This is a great opportunity. So my name's Colin, as Shreya mentioned. I'm a fifth-year PhD student here at MIT. I've been working on sort of heat transfer and energy conversion for a while now. Today, I'll be speaking a little bit about some general concepts in heat transfer and high temperature energy conversion that I've pursued through my academic career and that I find particularly interesting. So to start, so electricity is a vital and growing part of our world. I don't think anyone can argue against that. I think it's obvious that we also need to decarbonize our electricity sector, and that this need will become more critical as areas of the globe that are not currently electrified become electrified. There are a number of challenges that exist to producing electricity without CO2 emissions. How can we do this? How can we generate this power? When can we generate this power? Where can we generate this power? These are sort of the three big questions that I consider when thinking about this problem. So we have a number of solutions to solve for how to generate this. Solar PV, wind, nuclear. When we can generate it becomes a little bit more of a question. If you can only generate power when the sun is shining, doesn't really help you in the middle of the night. Then where can we generate it is another problem. Sunny places aren't necessarily where the power needs to be consumed. I think heat transfer and thermal engineering can address several of these challenges in some kind of unique and exciting ways. I'm going to try and share with you my experience with some of these topics. So first, I'll talk about heat transfer fluids, specifically applied to concentrated solar power. I worked on this project during my undergraduate research and a little bit at the beginning of my graduate school. I'll talk about concentrated solar power as well as the heat transfer fluids that are currently used for CSP, which are molten salts, and then a potential transition to a tin heat transfer fluid, and some experiments that we did with that. I'll then talk about thermal energy conversion, which is an essential part of how we produce electricity now, converting heat into electricity. There are a number of methods that we use currently that have been around for a long time and are very good at what they do. There are some new methods that have really been started to be investigated in the past 5 to 10 years. And one of the most interesting in my mind is thermal photovoltaics. So this is the direct conversion of heat to electricity without the intermediate mechanical step of motion. So many fewer moving parts, lower maintenance costs. There's a lot of advantages to this system. This can be treated as a standalone heat to electricity converter or integrated into a solar context to help provide a more efficient solar to electricity conversion. Finally, I'll talk about my current research into energy storage, focusing first on some cool, unique materials that we've considered for energy storage in the form of metallurgical grade silicon, and then focusing on some concepts about grid scale thermal storage that we're looking into right now. So to start with the heat transfer fluids, I'm going to take a step back when introducing concentrated solar power and talk about solar energy in general. So I think we're all on the same page that solar energy is great. I think just how great it is really the question. So there's a huge amount of sunlight that's incident on the Earth every day. In fact, there's about 1,000 times more light that hits the Earth every day than we consume as an entire world. And in the amount of power solar power that hits the world in 1 year is actually greater than all the reserves of coal, uranium, oil, natural gas on Earth. So this is a really massive, essentially unlimited resource. Even with that, only about 2.8 to 3% of global electricity is obtained from solar. So in this sense, solar energy is highly underutilized. There are a number of reasons for that, and concentrated solar power seeks to address one of them, which is the relatively low conversion efficiency found in solar PV cells. So concentrated solar power is a technology that was particularly popular maybe 10, 15 years ago, before the prices of natural gas dropped and before the prices of PV cells dropped. It's a very interesting technology that seeks to use the sun as a heat source instead of a light source. The way it works is you have a field of mirrors called heliostats in this configuration that reflect sunlight to a central receiver. This receiver has a heat transfer fluid that's pumped up through it, that's heated by the sunlight and stored in a hot storage tank. This fluid is typically what they call solar salts. It's a combination of nitrate salts, molten nitrate salts. Once this fluid is stored in the hot tank, it can be used as a heat source for a steam turbine, which is the same system that a coal plant or a nuclear plant would use, where the heat source in this case is the molten salt rather than nuclear fuel rods or burning coal. The advantage of this system over other solar energy conversion technologies is that it can run at night. Basically, you heat the salt during the day, and then you can run continuously, outputting power all throughout the night. The conversion efficiency from heat to electricity, or rather from sunlight to electricity in this context, is also much higher. Efficiencies of 30 to 40% can be expected for this system rather than around 20% for a standard solar PV cell. Fortunately, these systems are really unable to compete with PV cell these days in terms of cost. The cost of one of these systems, sort of per kilowatt hour of power produced, is around 10 cents. Just to give you an idea, the newest PV farms now that are being constructed around the world are on the order of 1 to 2 cents per kilowatt hour. So we're about an order of magnitude more expensive than PV right now. In fact, there are a couple of these plants constructed in the US, one of which in Crescent Dunes, which is nearby Las Vegas, was finished in around 2016. And it's actually already been decommissioned. It's already completely obsolete when it comes to converting solar energy to electricity. So this high cost is an important component of this system. And there are avenues to reducing the cost, and this is what this first topic was about, is let's consider all of the different components in the system, see where cost reductions can be made. And a significant cost reduction can be made by increasing the efficiency of the heat to electricity conversion step. And the best way to do that is to increase the temperature to enable different types of converters. Unfortunately, the salts that are used for this application have a maximum operating temperature of around 600 degrees Celsius. So solar salt, it's a nitrate salt combination. It melts at around 220 C. The maximum temperature is around 600 C, so we're pretty much constrained to that temperature range. It has very bad heat transfer performance as well, which I'll get to in a sec why that's important. But it is very low cost. So the idea of this project is, well, what are some alternative fluids we could propose for this that might improve performance and reduce cost of the overall system? So one that we found worked very well was tin. So tin, it's a metal. It has a relatively low melting temperature, right around where solar salt it melts. Its boiling temperature is very, very high. So it has a huge range of liquid. It has excellent heat transfer. It has very high thermal conductivity. There's a number of reasons why it's really excellent. Unfortunately, it has high cost, so you get these competing effects. To explain a little bit more about the heat transfer performance, if you look at this plot on the top right, x-axis is heat flux in the form of kilowatts per meter squared. And this essentially controls the size of the heat exchanger you need to dump this heat into water and make steam. So you can imagine it's inversely proportional to cost. So the higher your heat flux, the less area you need for your heat exchanger and the lower cost your heat exchanger is. And heat exchangers are a significant portion of the cost of these CSP plants. The y-axis is the ratio of pumping power, so how much power is required to actually pump this fluid through the system, to heat transfer ratio. And this is a function of a number of things, including the viscosity of the fluid, the thermal properties of the fluid. Anyway, a number of different components go into this. Basically, if your pump power to heat transfer ratio is 1, that means that for 100 watts of heat that you're transferring through your system, you require 100 watts of power to pump it. So you're basically going to be losing power in that situation. So you want that ratio to be significantly below 1, somewhere on the order of 10 to the minus 2, 10 to the minus 3. If we look across the graph on these lines, by switching from a molten salt to a molten tin heat transfer fluid, we can increase the heat flux by about 2 orders of magnitude, which reduces the area needed for the heat exchanger correspondingly by about 2 orders of magnitude. So that's a huge cost savings that we can get from that. Additionally, the higher temperature allows us to operate a much more efficient combined cycle compared to the Rankine cycle, which is typically used at these plants. So by switching from a maximum temperature of around 565 C, which is limited by these solar salts, to a maximum temperature of around 1500 C, which is now limited by the heat engine itself, or the conversion system itself. That's the maximum temperature for that. So we're no longer limited by our fluid. We're able to convert 60% of that heat to electricity now instead of 38, which results for the same size heliostat field, the same size tower, same size tanks, we can basically generate almost twice as much power. So that drastically reduces the cost of the electricity produced from this system. Now, unfortunately, even with this cost reduction, these systems are really still too expensive to be competitive in today's market. But we obtained a lot of really good information and learned a lot of great stuff about how to work with tin and its opportunities as a heat transfer fluid in other contexts. So we designed and fabricated our own pipes and fittings for tin made of graphite and tungsten. Figured out how to make pumps that can pump molten tin at very high temperatures. And we actually demonstrated pumping liquid tin at 1400 degrees Celsius in 2017. We published a Nature article about that, and also have the Guinness World Record for highest temperature liquid ever pumped. So this heat transfer fluid section, although the CSP approach that we were pursuing didn't end up working out, and we weren't able to get the cost to be competitive with PV, we obtained a lot of valuable information about how to integrate liquid metals into heat transfer energy systems. The next topic I'd like to discuss is on the thermal energy conversion step. So as you guys might have noticed from the previous step, the cost of these systems is highly dependent on the efficiency of the conversion from heat to electricity. So it's very important. That step is really the most critical step in the whole system design. So there are a number of existing conversion systems. Combined cycle was one of them that I mentioned. Rankine cycle was another. And I'd like to talk a little bit about kind of a new type of heat to electricity converter, or heat engine, referred to as thermophotovoltaics. So I've done some work on this, both in a context of thermophotovoltaics as a standalone heat engine and also integrating it into solar energy conversion. So let's start with thermal energy conversion at its core. So for those who haven't taken a thermodynamics class, there is a limit on the maximum efficiency of heat that you can convert heat to electricity. And that limit is basically governed by the temperature of your heat source. And it's a thermodynamic limit, takes into account entropy and a number of things. And the important thing to note is that going to higher temperatures almost always results in a higher efficiency. Now, this is important. This enabled this higher efficiency for the previous case with the concentrated solar power. And it's very important in the design of the various heat engines that we use to convert heat to electricity today. This plot shows a really great comparison, I think, of a number of different heat engines across a wide temperature range and a wide efficiency range. So there are some big names on here. The Rankine cycle, that's that steam cycle that I mentioned before that coal plants use and nuclear plants use. The Brayton cycle up here is what a natural gas turbine uses. And I'd like to focus on this thermophotovoltaics, so the high temperature, high efficiency region. I think this is a really interesting avenue of research. There's been a lot of developments on it in the last 5 to 10 years. So what are thermal photovoltaics? Sort of how does it work? So it's a solid state alternative to turbo machinery based systems like the steam engine or the gas turbine. It operates at very high temperatures, over 1500 degrees Celsius typically, can enable very high efficiencies, over 50% efficiency at low cost. Just to give you an idea of this cost, a natural gas turbine costs about $1 per watt of power output. So we're less than half the cost of a natural gas turbine, which is really sort of an excellent power producer on the market right now. So the way this works, if you look at the figure on the right, is you have some heat source at a temperature greater than 1500 degrees Celsius. It heats up this emitting surface, which actually gets so hot that it begins to emit a significant amount of light. So you can think of this like the filament in an incandescent light bulb. We're in that regime of temperatures. So a significant amount of light is emitted by this surface. It's about 1,000 times the intensity of sunlight, just to give you a sense. This light can then be converted directly into electricity using a PV cell. It's a specially formulated PV cell with multiple junctions, which is essentially two PV cells with different chemistries that are sandwiched on top of each other. So if we follow all of the light leaving the surface, a portion of it indicated here in orange, and also indicated here on the thermal emission plot, for those of you who've taken a heat transfer class, is emitted from this emitting surface and is converted into electricity by the top junction. Another portion that is unconvertible by the top junction is converted by the bottom junction. This allows for very high conversion efficiency of this convertible light. The rest of the light that can't be converted by either of these junctions is reflected back to the tungsten emitter and effectively recycled. We call this photon recycling. This is what enables this very high efficiency, 50% plus, compared to something like a solar PV cell, where even if you have multiple junctions, you can't recycle those photons that are unconvertible because they just get sent back into space. So I mentioned that efficiencies of 50% or greater are possible. The record thermal to electric efficiency for TPVs right now is around 29%. So there is a significant ways to go in terms of improving this technology. We're currently working on an implementation of TPVs that we hope will hit this 50% mark. And really, I think there's a lot of opportunity in this technology moving forward. Now, I've mentioned sort of thermal photovoltaics in a general sense. It's also possible to integrate this directly into solar energy conversion, with the idea being your heat source is actually concentrated sunlight. So you could imagine in that CSP plant with the receiver with the hot salt pumped up through it, you could just replace that receiver with this TPV unit and directly convert the light coming in to heat and then convert that heat into electricity. You could still actually obtain some significant efficiency gains. So basically concentrated sunlight is absorbed by a highly absorbing surface, which then heats up to very high temperatures on the order of 1500 degrees Celsius or hotter. There's then a separate emitting surface that emits light towards a PV cell. We can still capture this same photon recycling effect that I mentioned on the previous slide. And basically, instead of only being able to convert a portion of the solar spectrum, we're able to absorb the full solar spectrum. Now, there are numerous practical challenges with implementation of this. A primary one being this absorbing surface, it absorbs the sunlight, but it also releases light itself. So there's significant losses out of that front surface. It's also been difficult to demonstrate this system in reality in terms of parasitic losses. The record STPV that I'm aware of was actually done by a lab here at MIT as well, Dr. Evelyn Wang's lab. It's around 6.8% conversion efficiency from light to electricity. So that's significantly worse than the 20% expected with a PV cell. So we're really not winning here. But I think there's some potential for this system to really be developed further. And I think there's some really interesting applications involving spacecraft and things like that, where this technology might be really useful. So with that, I'll move on to the last section, which is what my current research is in, focused primarily on energy storage. Specifically, I'll speak about a silicon storage media that we're considering, and then some grid scale thermal storage concepts. So to start, I want to emphasize the need for storage as we move forward. The projected increase in renewables is, as expected, relatively significant in the United States, and these renewables are primarily in the form of solar and wind. Now, these resources are great. They're actually cheap now. They're cheaper than other options, but they're intermittent by nature. The solar power is only available during the day, and wind power can vary on the order of days or even weeks. So as the penetration of wind and solar on the grid increases, the need for storage of energy also increases. So this plot on the bottom right, there have been a number of academic studies looking into how much storage will we actually need. And the important numbers to look at is on the x-axis, we have basically what percent of the grid is provided by solar and wind. And the y-axis is the storage duration, or basically how many hours of backup power do we need if that percentage of our grid is solar and wind. So you can see there's sort of this ideal band that indicates the duration of storage necessary for a stable grid with high penetrations of renewables. So something like 70 or 80% penetrations of renewables, which is reasonably possible in the near future, still requires tens to hundreds of hours of storage to account for seasonal, not so much seasonal actually, more like daily or weekly variations in power. So current energy storage technologies are more or less insufficient to meet this need. So you can see we were on the previous slide, we were talking about hours or hundreds of hours. So of all the options that we have, the only two that really fit the bill are pumped hydro and compressed air energy storage. These are both mechanical methods of storing energy, and unfortunately are very geographically restricted. Pumped hydro is essentially the method of reversing the pump on a hydroelectric dam and pumping water uphill when you have extra electricity, and then letting it flow back down through the dam when you need extra electricity. And compressed air is a very similar concept, but you compress air underground when you have extra, and then release it out through a turbine when you need power. Both of these, as you might expect, are pretty geographically restricted. Pumped hydro requires a river and an elevation change, and this compressed air requires large underground caverns, which are not available in all geologies. So the next best option that we have are batteries, and there are 1,000 different chemistries of batteries, and new ones continue to be developed every day. And some of them are really quite excellent for what they're good at. Fortunately, they're still relatively expensive. They often require very exotic materials, and so they aren't really viable as a grid scale storage approach. They are not geographically restricted like the other bulk power management technologies are, but they're not quite suited for this sort of grid scale hours or hundreds of hours of storage necessary to enable high renewables penetration. Thermal storage, on the other hand, which is the storage of energy not as a mechanical energy in the form of water or air, or as electrochemical energy in the form of batteries, but storing energy, electricity in this case, as heat, has the opportunity to provide a low cost and high energy density solution that's not geographically restricted. So we think this is a really interesting field. It's an emerging field. There's been a lot of interest in it in the last 5 to 10 years. And we have some interesting concepts on how to capture this value. So the first concept I'll introduce is called thermal energy grid storage. We've developed this over the past couple years, TEGS for short. And basically we convert electricity to heat and then back to electricity on demand. And this seems crazy at first, as I just spent a whole number of slides telling you how conversion of heat to electricity is challenging and expensive, and it's worth investing in. So why would we basically reverse that process? Basically, the materials necessary to store energy as heat are so cheap that even if you pay the efficiency of converting heat to electricity twice, it's still worth it in the long run. So the way this system works is you have a cold silicon tank filled with molten silicon at around 1900 degrees Celsius, and a hot silicon tank filled with molten silicon at around 2400 Celsius. When you have excess power on the grid, you heat the cold silicon and pump it to the hot tank. And when you require excess power, you pump this hot liquid through a thermophotovoltaic power block. This thermophotovoltaic power block converts the heat to electricity, and that can be provided back to the grid and address any intermittency in renewables. The TPV panels are basically structured on this long stick that can be inserted or retracted from the hot region, the region with light, a lot of light. This allows for very rapid ramping of the system as well. So we can go from about 0 power to full power produced on the order of seconds, which is significantly better than other energy conversion technologies. So you may be asking, well, why are we using silicon in this application? And there's a number of reasons for that. And the primary one is that silicon is really, really cheap. So salts are inexpensive. Tin is significantly more expensive, but has better heat transfer performance. Silicon actually has a very similar heat transfer performance to tin, but at cost even lower than that of salts. Now, there are some practical challenges associated with silicon involving its high melting temperature. So it melts at around 14 degrees Celsius. So freezing is an issue. If any part gets below that temperature, that becomes a problem. Another big problem with it is that it's a lot more reactive than tin. So tin is very nice and stable, specifically with the materials that we've have experienced it with, graphite, a main one. Silicon, unfortunately, does not have quite the same level of stability with graphite, which is basically our real workhorse in terms of piping and pumps and containment and everything. It's a great high temperature material. It's very strong, high thermal shock resistance. So being incompatible with graphite is kind of a deal breaker for this silicon. So it turns out carbon and silicon form silicon carbide, which is a ceramic compound of the two when in contact with each other at high temperature. And it turns out that if you contain molten silicon in a graphite crucible, it actually forms a self-sealing barrier of silicon carbide where the silicon and graphite interact. So this silicon carbide layer forms, it thickens, and then it essentially prevents silicon from getting through, and it prevents carbon from getting out, and basically stops that reaction in its tracks. Now, this is a great solution because we're now no longer worried about silicon and carbon reacting because they're not even touching each other. They have this intermediate layer that's able to shield them from each other and prevent these reaction problems that we've predicted. So we tested this both in a small situation. This is on the order of 1 inch in diameter in an induction furnace. And then we also tested it in a larger tank. This Air 14 is a reference for the grade of graphite we used, which is very important. If it's too porous graphite, then that layer is unable to form quickly enough, and a lot of silicon is able to penetrate deeply into the carbon. And in both of these cases, a protective silicon carbide layer was formed, and it prevented any more silicon from reacting with the carbon. So far, so good. Everything looks like it's working out. It looks like we can contain the silicon and carbon, and it forms a protective layer, and we have no problems. Unfortunately, when we went to design the pump, which is an essential part of this system and probably the most challenging part as well, we realized, okay, things aren't quite as simple as it seemed. So these 3 pumps are actually 3 separate experiments, which are operated at a temperature of around 2150 degrees Celsius for different periods of time. And what we saw in these 3 cases is that Although we were able to pump relatively well for short times, 0.1 hours to 1 hour, when we went to the 10-hour case, you can see this gap right here. It's significantly thicker in this case than the other two cases. And what's happening is actually the bottom edge of this impeller is corroding. Basically, it's forming silicon carbide, and that silicon carbide is being torn off through frictional contact and then forming a new layer of silicon carbide. So this basically eliminates that protective skin that we observed in previous experiments and becomes a serious problem. So essentially, based on these experiments and a number of experiments done over several months, we determined that silicon is really impractical as a heat transfer fluid or thermal storage medium in this context because it's just too difficult to contain and pump it. It's too reactive, dissolves carbon like crazy, and it's really just a not the best option for this. So we took a step back to reevaluate our approach and approach it from a view of, well, what do we know works? And we know that tin works. We know that we can contain it in graphite. We've demonstrated that, we're experienced with that, and we know that we can pump it. So how could we combine the expertise that we've obtained through the CSP work that I talked about at the beginning with the high temperature heat transfer fluids and this TPV-based thermal storage system? So we devised TEGS 2.0, or tin TEGS as we call it. So two components of this system are very similar. The heater, we're still charging from the grid. We're source agnostic. You can use any type of power source. The thermal photovoltaic power block also remains the same in basically any way. The only difference is this actual storage unit. So instead of being 2 tanks of silicon, it's now just a bunch of blocks of graphite. So graphite we know works well with tin. Graphite also has a very high specific heat. It's a great material for thermal storage. It's relatively cheap. So basically what we do is we heat the tin with power from the grid. We use that tin to heat these graphite storage blocks. We're still oscillating between the same temperature range, 1900 Celsius and 2400 Celsius. Then on demand, we can pump the tin back through these power blocks, pump it to the thermophotovoltaic power block, and produce power. Now, this iteration of the technology has a relatively high energy density. It's about twice the energy density of lithium-ion batteries, so it requires about half the volume, which enables a very large capacity for a pretty small footprint. It has low maintenance, very few moving parts that come from this thermophotovoltaic power block. It has a fast ramp rate that comes from being able to insert those PV cell sticks in and out of the hot block. And we estimate it's about 1/10 the cost of lithium-ion batteries based on the really simple, inexpensive materials needed to construct this. And that takes into account this 50% conversion efficiency loss that we may take in our thermophotovoltaic power block. So to go a little more detail into the cost comparison, we considered 2 cost metrics that are typically used for storage technologies. The first is levelized cost of storage, which is effectively the total cost of the system over its lifetime divided by the total amount of energy that the system will store over its lifetime. So if you cycle it more, the denominator goes up and your levelized cost of storage goes down. If you pay less for the system, same thing. Now on levelized cost of storage, our system is very, very competitive on cost. It's significantly below, about an order of magnitude lower than the top 3 battery technologies, which are lithium-ion, lead-acid, and flow batteries. Additionally, in the capital cost per energy capacity, that's another metric people often use to evaluate storage technologies. This is essentially how much does it cost to build 1 megawatt hour or 1 kilowatt hour of this system in my basement, or in a plant, or whatever context you'd like. And in this context, we're also cheaper than lithium ion. So in either a 10 megawatt, 100 megawatt hour version or 100 megawatt, 1 gigawatt hour version, this TEGS system is about an order of magnitude cheaper. Something interesting to note here is that the costs for the larger system are about half the smaller system. And that primarily has to do with the fact that as you scale up, your insulation cost goes down because your surface area to volume ratio decreases. So you can think of it in the same way that a small person gets cold faster than a large person. Um, that yeah, essentially, yeah. So basically, there's an advantage for scaling up to very large sizes. So based on the really favorable economics of this system, we're trying to pursue a path to commercialization. So we have some existing funding from ARPA-E. We received a grant to develop this technology further. We also have some collaborators at NREL that we're working with to develop custom PV cells for our application. We've had demonstrated interest from the DC Department of Energy, as well as Solero, which is a PV cell manufacturing company on they've demonstrated interest in helping fund a pilot scale demo of this system. And then we're looking for potential partnerships in the future to help take this commercialization further. So with that, I'd like to acknowledge a number of people that have made all this work possible. I'd like to acknowledge my advisor, Dr. Ashegun Henry, my lab mate, Caleb Ami, who now actually works for the Department of Energy, our colleagues at NREL, as well as various other people at MIT that have worked with me over the years. I'd like to acknowledge our funding source, ARPA-E, as well as the funding source for my previous solar TPV work, which is the Solid State Solar Thermal Energy Conversion Center. So thank you all for listening, and I guess I'll take questions from Shreya now.
Hi, thank you so much for that talk, Colin. It was really interesting. I'm sure everyone learned a lot from it. So the way the Q&A will work, I'll state from before, is if you have a question, just type it into the Q&A box on the bottom bar of the Zoom call, and I will read them out in chronological order so Colin can answer them. So we have a question that came in while you were talking, actually, from Sarah. She asks, to prevent the silicon from freezing, would you have to expend additional energy to maintain the high temperatures? Would a significant be needed for this purpose, even when there's high grid demand?
Yeah, so we designed the thermal storage component, so the silicon tanks, or in the case of the TEGS 2 or TEGS or TEGS 2.0, the graphite blocks, to lose about 1% of their thermal energy per day. So this enables daily and weekly storage pretty nicely. If you wanted to store energy for a very long period, like over a course of months, it probably wouldn't be the best technology because, as you mentioned, you'd have to continue expending energy to keep it topped up. But on the order of days or weeks, it's really not so much of a problem.
Great, thank you. We have another question. How do you insulate the thermal storage units? Is there a significant loss of energy?
So I think I answered the second part of that. So insulating things at this very high temperature is actually quite a challenge. And for those heat transfer people in the audience, basically at this temperature, radiation is the dominant mode of heat transfer. So you could have a complete vacuum gap between your thermal storage media and the outside wall, and you still get a huge amount of heat transfer. So the way you get around that is basically by having as much material as possible between the two surfaces. So it's a very interesting because it's the total opposite of what one would expect for lower temperature insulation. So actually the highest performing insulations for radiation are like powder-based insulations, where you basically just have a bunch of powder compressed into this solid that has a bunch of tiny little surfaces that help effectively reflect some of the radiated light. So we actually use a combination of 3 different types of insulation. So the first is actually a graphite sort of felt. So it's like, you can imagine just felt, like normal felt used for crafting, but made of graphite. So, and then the second layer we go beyond that is an alumina base. So aluminum oxide is a compound with aluminum and oxygen. It's a ceramic. It's very high temperature compatible. So we use a pretty thick layer of that. And then we use a silica or glass-based insulation on the outside. So it's a multi-layered stack that corresponds to the cost, thermal conductivity, and temperature rating of each material.
Great, thank you. We have another question. Are you imagining the thermal photovoltaic system as a grid level storage solution or individual home level storage solution?
Yeah, so I think I don't think it's really going to be economical for the home level storage. So as I showed on the previous slide, going from 100 megawatts or 1 gigawatt hour to around 100 megawatt hours is a doubling in cost. That gets worse. You can imagine as you go smaller and smaller. So yeah, I don't think like 100 megawatt hours is a huge amount for a home. Like it's way more than a home would ever need. So if you go to something small like a Tesla Powerwall size, I think it's really going to just become cost prohibitive. You'd need so much insulation to keep it hot that it wouldn't work out.
Thank you. Next question has a little compliment in it. Nice talk. Thank you. The question itself is, what is the overall system efficiency? Is this system applicable to distributed microgrid applications?
Yeah, so basically the conversion of electricity to heat is almost 100% efficient. And then we estimate we lose only about 1% per day in parasitic heat loss through the walls. So the round trip efficiency, as it's often called in the storage field, is really dominated just by this heat to electricity conversion. So we estimate around 50%. I think it is applicable to certain microgrids. I think it depends on the size of your microgrid, as I mentioned. I think like a small town, yes, it may work in the 100 megawatt hour context. In a context of like a compound or like several homes, probably not so much.
Thank you. Our next question is from Simon. How difficult would this thermal energy storage system be to service? And how much downtime would be required to allow the system to cool the serviceable temperatures and then reheat to the operation temperature?
Yeah, that's a very, very good question. So the entire system is actually encased in an inert containment atmosphere. So you can imagine it's in a big welded steel box. And the reason that is all of this graphite would, if exposed to oxygen, would basically burn. You can imagine it's basically like coal, and it's super hot. So if you introduce oxygen, it immediately oxidizes, which is in and of itself an exothermic reaction. So you'd basically light the whole thing on fire. So it is a challenge to service. That being said, the need for service should be relatively minimal. This is not a complex system. These are very simple materials, simple geometries. The pump is really the main source of failure. And the way they get around that in current CSP plants is they basically just install multiple redundant pumps. They run one, and if that one breaks, they move on to the next one. And over the 20-year lifespan of the plant, they expect to go through a few pumps, so they put a few in when they're installing it.
Thank you. Our next question is from Samuel. How will the energy market pay for these massive thermal storage technologies? Energy arbitrage, buy low, sell high, or through some other ancillary services market?
Yeah, that's also a really great question. Basically, right now, the way the markets are currently structured, it's very hard to make money with a long duration storage device like this. And I think a big part of this has to do with the fact that, as we saw on one of the previous slides, this longer duration only really becomes critical when you approach 50+% renewables penetration. So the demand isn't really there. So the markets haven't developed to account for that. There are several avenues that you can bid into with this. So buy low, sell high is one option. It's sort of inherently an unsustainable option. And the more storage you build, the less effective that becomes. So I don't think that's really a good long-term option. I think it will probably find its way in the form of capacity markets, which are currently serviced primarily by gas peaker plants, which are inherently inefficient and expensive and will be retired at some point. So we think that replacing these gas peakers with systems like this could be a great avenue to sort of capture that value stream.
Thank you. Next question is, Are there no materials that could work as alternatives to the graphite surfaces that react with the silicon? Could the low cost of the silicon permit higher costing materials for the pipes/pumps?
Yeah, that's a great question. So So the materials challenges at high temperatures are very interesting because things become a lot more complicated because reactions happen very quickly. So basically, if two things are not in thermodynamic equilibrium with each other, um, the reaction will occur almost instantly. So any sort of decomposition um, of materials or reactions occur extremely quickly. So the more elements that you introduce into the mix, so maybe some special ceramic coating or things like that, the more opportunities you have for these various reactions. Even if the equilibrium is only a small portion of the ceramic dissolving in the fluid, that dissolution will happen immediately and will continue happening as you pump this liquid over it. So it's really very difficult to have any sort of complex compounds in there. So we try and stick with really base um, like single elements. So in that context, there's really not much else that works. Basically, the options you have there are tungsten or graphite, um, and tungsten has a dissolution problem in silicon as well. So it's a challenge. It's a definite materials challenge, and I'm not a materials scientist, and I don't pretend to be. So I don't understand all of the intricacies of those reactions, but we do have materials scientists that we work with, and it's something we've been unable to figure out.
Great, thank you. We have a question from Arena. A lot of new energy technologies face criticisms of their safety and reliability when they're first introduced, for instance, nuclear. What safety/reliability challenges do you foresee with thermal storage?
Yeah, that's a good question. So safety wise, I'd say it's the same level of safety as something else that's this big and hot. So, comparable situations would be like a blast furnace in steel manufacturing, or the boiler in a coal plant or something like that. So it's a big hot bunch of hot material. That being said, in Tintex 2.0, the one with graphite, um, there's very little liquid. So really, even if you spring a leak somewhere in the system and you start to leak this tin out, there's actually very little tin that's included in the system. And this is by design because tin is expensive. So there's not a whole lot of stuff to leak out and spill all over the place. And the stuff that does leak out is non-toxic. I mean, tin was used for silverware and things for a long time. Um, so I don't think there are so many safety concerns. There's also less of a thermal runaway concern compared to lithium ion. Um, Sort of what you have is what you get. You have a bunch of heat stored, and you just have to make sure that if all that heat is released over a period of time, it doesn't damage anything nearby.
Thank you. So for all our attendees, in order to end on time, we're going to take the last three questions asked in the Q&A box, and Colin will answer those. So we have a question from Rashid. Could you talk about load following on the TPV power blocks a little bit more? The
Yeah.
panels can be inserted or retrieved depending on the power demand.
Exactly. Yep. So basically, it's a pretty much linear proportion between what percent inserted it is and the percent of the maximum power output that we can obtain. So yeah, so you could imagine you would have a linear actuator on that PV cell stick, and it could be actuated very quickly on the order of a second or less. So you could really very carefully load follow both on the supply and demand side.
Thank you. Next question is from Raymond. I might have missed this if you touched on it in the bit on insulation, but are there any safety concerns with operating such high heat storage systems, particularly compared to other energy storage solutions?
Yeah, I mean, there are safety concerns. I think, as I mentioned, it needs to be treated with respect like anything else of this temperature and size. I think there aren't really chemical safety concerns in the same way that other plants might. There aren't radioactive safety concerns, and there aren't really any sort of disaster or problems would presumably be isolated relatively close to the region. So if something like a hydro dam breaks, it floods the entire downstream area. If a nuclear plant melts down, it destroys that entire surrounding area. Coal plants release clouds of smoke into the environment. So I think on the scale of safety hazards in energy generation and storage and moving it around, I think this is pretty low.
Thank you. And our last question for the night is, what is your advice for undergrads to get involved in research like this?
Yeah, so I think step one is find a professor who's doing research that's interesting to you and email them. I mean, we love having undergrads in the lab. It's really great to be able to teach someone and have them contribute to a project. I had a really great undergrad research experience. So I would reach out to my advisor, or you can reach out to me directly. I guess I'll put my email in the chat. And yeah, I think just reach out and say, hey, I really like your research. Like, can I help work? And if you show up and you work hard and you really try and learn something, then they'll love to have you in the lab. There's always work to be done.
Thank you so much. And for those of you who are listening, Colin did put his email in the chat box, and you can access that if you would wish to. Thank you, everyone, for coming out tonight. Thank you so much, Colin, for the incredible talk. I learned a lot. I think we all learned a lot.
Thank
and
you.
Looking forward to the rest of Choice Days and getting ready for Energy Hack.
Yeah. Enjoy, everyone.
Thank you.